Going to do a little bit more average velocity to start with today. If you climb to the top of the Tower of Pisa, pause. Don't climb to the top of the Tower of Pisa. I don't know, the next few months, not a good idea. Wait a little while and then go visit Pisa, okay? All right, we're going to climb to the top of Tower of Pisa at some point in our lives, just not anytime soon. And we're going to drop a coin to the ground, and we're going to estimate the instantaneous velocity at t equals 0.7 seconds. All right, so we're going to give an estimate of an instantaneous velocity. So previously we've been doing average velocity, and that's what we're going to do right here. We're going to find average velocity between points. So let's fill in this chart to start with. It says instantaneous velocity at 0.7 seconds. Use the formula 16t squared to compute the average velocity. So this is going to be our function, just like we've been using, and we're going to use this function and these different time intervals to come up with our average velocity. So first one would be, okay, so we got s of 0.71 minus s of 0.7 over 0.71 minus 0.7. And, that would be 16 0.71 squared minus 16 0.7 squared over 0.71 minus 0.7. And you punch all that into your calculator and you get the magic number 22.56. So that's the average velocity of that coin at 0.7 seconds. Between 0.7 seconds and 0.71, that's the average velocity. 22.56 feet per second. Okay. If we're going to do the rest of these, I would take 0.7, go right there, 0.701 right there. Notice each of these is getting to be a smaller number. Okay. So each of these is a smaller number. These numbers are getting a lot closer to this number. So yesterday, the day before, we're doing average velocity, and I picked some random numbers for you to find the average velocity between, but we're kind of choosing numbers with a purpose here. We're getting numbers that are close together, okay? So if I were to plug these two into my average velocity formula, I would get 22.416. Plug these two in, I'd get 22.4016. Plug these in, 22.40016, 22.40002. So I think that one rounded, that one should be a 16, but we'll leave it at that. Okay, so that's filling in the chart there. And it wants us to estimate the instantaneous velocity. And we'll get to that here in a second, but for now, we found the average velocity, we're good. Okay, and instantaneous velocity is more like, driving a car, when the cop does the laser at you and says, oh, I got you going 58 and 35, and you're like, oh crap. Well, sir, my average velocity was only 38 miles per hour between the time intervals of when you zapped me and when I slammed on the brakes. That's not really how that flies. So instantaneous is what we're looking for here. We want to know exactly how quickly this thing is falling at 0.7 seconds. So we're going to give a good estimate here in a little bit. So let's slide down. When we talk about velocity in our daily lives, we normally describe it as instantaneous velocity. Just said that. We describe cars. Just said that. Trains, didn't say that. They have those in Italy. Airplanes, didn't say that. They have those everywhere. And baseballs, they don't have that anywhere right now, as traveling at an instantaneous velocity rather than an average velocity, just like I said with the cop and the laser and all that kind of stuff, which could be faster or slower. So your average velocity could end up being faster or slower, just depending. Why can't we define instantaneous velocity as a fraction like we did on the previous problem? So when we do this, we pick two numbers that are really close together. But if I wanted instantaneous, if I wanted to know between 0.7 and 0.7, that's a problem. Why is that a problem? Because when you do this, f of x2 minus f of x of 1, you get, 0.7 minus 0.7. Your denominator would be 0, and you can't do that. That's a problem. Well, how could we estimate what an instantaneous velocity would be? Let's just make it the get really, really close to 0 on our time interval. Okay? The second really is important there. Get really, really close to 0. I feel like that's the donkey on Shrek. Is that really, really? I think so. If there was 30 of you, one of you would know the answer to that. Generalization, but instead, here I am talking to myself. Really, really. Generalization there. Average velocity over a very small time is really, really close to instantaneous velocity. So let's write that. Average velocity over a, let's say really, really again. Average velocity over a really, really small time frame. I don't know why I put a comma there. I don't know how to change it. Is close to instantaneous velocity. So it would give us a good estimate. If we made our time interval really, really close to 0, that would give us a really good estimate, which is what it was asking for up here. Give me a good estimate on what our average, or our instantaneous, give us a good estimate on the instantaneous velocity at 0.7 seconds. Well, if I'm looking at this thing, we're getting really, really close to 22.4, right? So when I come down here and it says, given the Tower of Pisa chart above, what is a good estimate for instantaneous rate of change at 0.7 seconds? I'm going to say 22.4 feet per second. If you are really good at Excel for whatever reason, you took those classes, or maybe you're just a really big loser and you like to deal with large data sets, we can look at this just for 2 seconds. If you notice, I put the 0.7 on the far left column. I put the 0.71, 701, all that kind of stuff in the C column. And then on the E column, I punched in the displacement, so the squared stuff right there, minus just the, I guess the squared stuff of the first column, the 0.7, so 16.7 squared. Then I found the displacement, I subtracted the 2. And then I put the time interval over on column L, and then I punched it into my Excel spreadsheet and ended up with the answers. All right, let's slide down here. In the previous examples, when we made the time interval shrink to 0, we can say that the instantaneous velocity is the limit of the average velocity. Man, I sound so smart when I use the word limit. The instantaneous velocity is the limit of the average velocity. So limit just meaning we're getting really, really close to a number when we do all these average velocities, okay? Our limit ended up being 22.4. We're going to define that more here in a little bit. Algebraically, the average rate of change. I feel like we've done 100 of these. Okay, that's my algebraic average rate of change. Graphically, the average velocity is the slope of the secant line. Secant line, geometry. Hopefully you had a really good geometry teacher. Some of you did, some of you didn't. Sorry, Marilyn, you did not. Slope, rise over run. That's pretty much what you're doing here. Change in y's over change in x's. So the average velocity is the slope of a secant line. Secant line means touches it twice, touches the line twice. Using the graph below, find the average rate of change from A to B. Okay, A is right here, B is right there, so I'm gonna put a point right there, and then a point at B over here. And if I wanna find the average rate of change between those two, I'm gonna draw the line right there, and I would find the slope between that. I don't know what it is, maybe like 1/4 or something, just depends on what each of those units is. So that would be the average rate of change between A to B. Maybe 1/3 or 4, maybe 1/3, sorry. Next, I want you to change something really quickly. I want you to change this from A to B, and I want it to say at C, okay? So algebraically, to find instantaneous speed or velocity, we need calculus. Graphically, the instantaneous speed, all right, let's go back. Graphically, the average velocity was the secant line right there, the slope of the secant line. The instantaneous velocity or speed is the slope, rise over run, of the tangent line. Tangent means it touches the circle at one point. Sorry, Marilyn, you didn't have a good geometry teacher. You don't know what that means. At a specific point. Using the graph below, estimate the instantaneous rate of change at C. Well, if I'm at C right there, I don't know. It's, if I want to know the slope right there, it'd be maybe kind of like that. I'm okay with that, other than that arrow right there. That's pretty crappy. That'd be the slope right there. And I don't know, you'd take, 2 points somewhere on that graph right there and pick you a point out, and you'd find the slope. I don't know, like what rise is maybe 1 1/4, 1 1/2 over 2-ish. So I'm not looking for anything specific there, just so that you know that we're looking for the slope of this line. It's tangent for instantaneous. Secant, slope, average. Okay, those are the 2 important things right now. All right, let's flip it over on the back. Okay. A roller coaster has its largest drop modeled by the equation. Story time. This one's for you, Riley. Me and Mrs. Briscoe went down to Busch Gardens at some point. I don't know. It's been 5 years or so ago. And Mrs. Briscoe had never been on a roller coaster that went upside down. They have this roller coaster that I'll probably post a link to on the website that I talked her into. She made me promise on all types of things. This thing does not go upside down, right? No, Laura, this thing does not go upside down. You promise? Yes, I promise on blah, 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 that kind of stuff. And we get up there, and I knew I had lied, and it is going upside down. Conveniently, I had put us on the front row. So we get up there, and we're on the front row, and this thing is bad. It is awesome. And she went on a roller coaster for the first time. She went upside down, and yeah, it was a pretty steep drop. Like, it holds you up there. Anyways, I don't have time. My battery's dying. So I'll post a video of that so you can watch exactly the roller coaster that went on. First upside down roller coaster for Mrs. Briscoe. And yeah, I've already wasted a minute and a half. Roller coaster has its largest drop modeled by the equation below, where d of t, so that's like our f of x, where d of t is measured in feet and time t is measured in seconds, okay? So has its largest drop modeled by this equation. So this equation is measuring our feet per second during this largest drop, okay? So find the average velocity of the roller coaster from 2 to 8 seconds. You know how to do this. Average velocity would be, we got 8, so d of 8 minus d of 2 over 8 minus 2. And if you punch, I'm going to save you the time on this, because if you were to punch all of that garbage into your calculator, you would get 63.47 feet per second. Okay. All right, let's find the average velocity between 4 and 6 seconds. Now would be a good time to pause and see if you can do this by yourself. You got d of 6 minus d of 4, and you say 6 minus 4 down there, and you punch all that garbage into your calculator, and you get 48.51 feet per second. Now, this is average over these time intervals. We're not looking at instantaneous just yet. We're looking at over these time intervals, just the average velocity in this drop. Okay? It's fairly fast, I think. I don't know what an average velocity is on a roller coaster in general. I feel like it's like 45 miles an hour, maybe. I don't know. Over here, a roller coaster, same kind of deal. So the same formula, estimate the instantaneous velocity of the roller coaster at exactly 5 seconds. So we're going to estimate the instantaneous velocity when it's at 5 seconds by doing this chart. Okay. So on your scratch sheet of paper, you're going to come over here and you're going to do what? D of 5.1 minus d of 5 over 5.1 minus 5 to find the average velocity between those two. When you punch that into your calculator, you will get 47.3997. Now would be a good time to pause this video and do the rest of them to make sure you know how to do this, so that when it comes time on all that delta math garbage that you love to do, you'll know how to do it and you won't poop yourself because you don't know how to do it. So I would do that for each of these. Notice my time interval is getting smaller. I'm getting really close to being able to estimate an instantaneous velocity. So I plugged in all these numbers. It only took me like 2 days to do all this. So 7142. This is 46.6474. 46.6. Whoop, that should be 641. So if we're going to estimate the instantaneous velocity, I'm going to say that the instantaneous velocity is getting really, really close to what? 46.6, maybe 46.4. So let's say instantaneous rate of change or instantaneous velocity is going to equal, let's say about equal, what do you say? 46.6 feet per second at time equal to 5. Explain the meaning of instantaneous velocity in the context of the question at 5. We just did that. So the instantaneous rate of change, the instantaneous velocity in the drop at that particular point is 46 miles an hour. You could be going faster, slower before and after that, but at that particular moment, you're going about 46.6 feet per second. All right, next example, we got, oh gosh, sine. Where does sine start, people? In the sand. You're gonna get that right on your entrance exam, wherever you go. UGA, Abigail, Ms. Palmer, Mr. Myler, you're gonna get that right on your entrance exam. You're gonna exempt your pre-cal stuff. Where does cosine start at? In the clouds. Good call. I guess you got it right, I don't know. Once again, I'm talking to myself. The traffic flow at a particular intersection is modeled by the function f, defined by all of that kind of stuff. So we got traffic flow at an intersection defined by this sine function. So remember sine? Whee, go something like that. And we've done some transformations to it. But, you know, the idea is that traffic is going faster at sometimes it's going slower, sometimes going faster, sometimes it's going slower. That's why the sine function is good for this, to represent traffic flow. All right. So where f of t is measured in vehicles, so our answer will be in vehicles, and t is in minutes. Okay, so t is in minutes. So we're going to be looking at what, cars per minute maybe? Vehicles per minute, sorry. Got some, you know, trucks out there, and sports utility vehicles, or perhaps bicycles. I don't know what else you can drive these days. Miniature van. Find f of t for t equals 8. Make sure it's in radian mode, obviously. Make sure it's in radian mode when you're plugging stuff in right here. F of t so I'm just gonna find f of 8. That one's fairly easy. 92 plus 5 sine of 8 over 2. Punch that in and you get f of 8 equals 88.2. What is that? Cars per minute, is that what we said? Yeah, cars per minute. So if I was looking at the graph, you know, this squiggly line on a graph like Desmos or something, and I looked at 8 on the x-axis and I went up, then I would say, oh, it's at 88.2. Okay, that makes sense. What is the average rate of change of the traffic flow over the time 10 to 15? So this looks a little bit different than what we've been doing. We've been seeing it as this, 10 to 15. Same kind of deal though. When we were talking about domain and range, same kind of deal. You can write it like that. Indicate your units of measurement. We already talked about that. That would be cars per minute. So let's just write it out like this. This would be f of 15 minus f of 10. The capital F is really throwing me off here. I got to change that. 15 minus 10. And, you know, f of 15, you'd punch that in, minus 10, punch that in, subtract them all over 5, I guess. And you'd get 1.897 cars per minute. Man, average rate of change from 10 to 15 minutes. So 1.897 cars per minute. That sounds like so much fun. Let's look at the next one. Estimate the instantaneous rate of change of traffic flow at t equals 8 by finding the average rates below. So once again, we're going to do a bunch of average rate of changes here. Now would be a good time for you to pause it and to do all of this, you know, making sure that you've got this, because your assignment on Friday is going to have to do with average rate of change, average velocity. So you need to make sure that you know how to do this, okay? Spoiler alert, we're gonna get some negative numbers. When I plug these in, I should get, so once again, let's say this, f of 8.1 minus f of 8 over 8.1 minus 8. We're looking for an estimate of instantaneous speed, rate of change, velocity at t equals 8. Okay, so we're looking to estimate our rate of change at t equals 8. So we're going to get really, really close numbers to 8. I guess I could have done 7.9999. I don't know why I didn't do that. If you want to challenge yourself and or you want to be one of those people, do 7.99, 10.999, 10.99, 10.9. All right. This would be negative 1.5861. This would be negative 1.6293. This would be negative 1.6336. Negative 1.63403. Well, it looks like if we're going to estimate it, it's going to be our instantaneous rate of change. Oh man, that was going to be like one of those weird equal signs. That was rough. I don't know what that is. That was like a W. I got negative 1.63 cars per minute. What does that mean? That means that the rate is slowing down. The rate is slowing down. All right, last one on this page. An object dropped from a state of rest at time t equals 0, travels a distance of s of t equals 4.9 t squared meters in seconds. Okay, so this is our function. How far does the object travel during the time interval? How far does it travel? That would be displacement. Okay, so that's just the top part of my, you know, when I do all this kind of stuff, like it's just the top part, displacement. How far did it travel? So I'm just gonna say it's S of 3 minus S of 2.5. When I punch that into my calculator, I get 13.475 meters. That's how far it traveled in that half of a second. Wow. Find the average velocity of the object. So this would be the whole thing. I would say s of 3 minus s of 2.5 over 3 minus 2.5. Punch all that into my calc. Remember, I'm plugging 3 into that, 2.5 into that, and then dividing by that. I would get 26.95 meters per second. If I'm wanting to find an instantaneous velocity for this thing, so just a second ago we were doing between 2.5 and 3 seconds, found an average velocity over here. Now we're going to find estimate, please forgive me, estimate an instantaneous velocity at 2.5 seconds. Okay, same function, got to estimate an instantaneous velocity. So gonna make this denominator really close to 0, my time interval really close to 0 by doing all these decimals. So I'm going to do all of the, so for this one I would say, what, s of 2.51 minus s of 2.5 over 2.51 minus s, nope, just 2.5, sorry. Punch that in my calculator, and I would get 24.549. The next one, do the same thing. 24.5245, 24.5, and then I think you get like some zeros and stuff, and then on the next one I think you get 25 and like 24.5, and then several zeros, maybe like 1, 2, 3, and then some 4 nines or something over there. So instantaneous rate of change is approximately 24.5 meters per second.